Topic 5 focus on the pollution control, which specifically talk about the targets. So in other words, we want to know how much the pollutions are we willing to tolerate in order to allow for economic growth. So if you look at this image on the right side, so this is the case of China. So they are actually having a serious air pollution problem because, for your information, China is one of the giants economy and China wanted to expand its economic growth. So because of that, they are willing to accept this serious air pollution problem. Why do we have to be concerned about pollution if pollution can allow us to achieve economic growth? So the first reason is that the health costs of pollution are actually very large. For instance, outdoor particulate matter pollution causes more than 3.2 million deaths per year. Believe me, if you have a lot of money, you will not be happy if you are actually ill. So money cannot buy your happiness, right? Second, investors often don't want to live in polluted cities because they know that if they are living in that polluted cities, their health will be affected. And the tourists are also less likely to visit in that area because normally the sceneries are not nice. And many people are less likely to go out because they know that when they go outside, their health will be affected. Okay, so 75% of managers, this is just the examples, in Hong Kong cite that the pollution as a problem for retaining talents, people talents. And this is their statement. We could be doing this in Hong Kong, but none of the directors want to live there. That's the cold hard fact. So these statements are made by the director who moved his operation to Singapore because he knows that their operation cannot be sustained or cannot be operated in the polluted area. Economic activity and pollution damage. Some of our economic activity can lead to emission to the environment. So some of these emission can be absorbed by the environment while some of them cannot be absorbed by the environment. So these non-absorbed emission can be in the forms of stocks and flow pollutant. So some of the stock can degrade while some of them can't. And the stocks and flow pollutant can actually damage the environment. So when we want to analyze the stock pollutant, we may be thinking of the time effects, for instance using optimal control optimization method. While when we want to analyze the flow pollutant, we can just use the static effects. So time here is actually not really important. Damage from emissions depends on a few factors. The first one is assimilative capacity of the environment. It means that how well the environment can take the emissions. Some of the emissions can be absorbed quickly. For instance, if you put small amounts of salt into a river, it can be absorbed quickly. But if you put a lot of salt into the river, we may cause a lot of trouble. Second, existing loads on the environment. If let's say our current existing environment is already in a deep stress, giving small amounts of pollution can cause lots of trouble. Third, the number of people living in the area. So many people will cause more damage compared to small number of people. The next one is the taste and characteristics of the affected people. Some people are very concerned about the environments and the emissions. So these types of people will cause smaller damage compared to those who don't really care about the emission. And the last one is the rates of decay of the pollutants. Some pollutants can decay very quickly. So we can actually accept this kind of pollutant even though it is in a large amount. Okay, so how long the pollutant hang around? So for sulfur, it can hang around 7 days or less, while for HRC or hydrofluorocarbon, it can stay up to 260 years. So if let's say we emit it right now, so our great great grandchildren can still enjoy it, right? Flow versus stock pollutants. Flow related to the damage from the flow pollutants. And for the flow pollutants, the pollutions are actually depends on the emission level. If let's say the emission is zero, the pollution is also zero. The examples of flow pollutants are like noise or light pollution, and their lifespans are actually very short. So sulfur emission is also considered as the examples of flow pollutants because they can also last for a few days. So stock related to the damage caused by the stock pollutants. So the accumulations of the stock pollutions occurs when the residuals have a positive lifespans and the emission produced are actually at the higher rates, which is actually exceed the assimilative capacity of the environments. The examples of stock pollutants are like metals, mercury, leads. And for your information, the assimilative capacity of these pollutions is actually zero. And some of the examples of stock pollutants are like non-biodegradable rubbish, greenhouse gases. So stock pollutants are very harmful to human health, structures, agriculture, and marine life because stock pollutants have a long lifespans compared to the flow pollutants. Different ways of thinking about pollutants. Uniformly mixing. This is the types of pollutants that quickly disperses to the point at which its spatial location is not really an issue anymore. So greenhouse gases are like this. It doesn't matter if carbon dioxide is emitted in China and India because they both will be adding to the global stocks of carbon in the atmosphere. So locations or the source of pollution is not relevant here because the pollution will be evenly distributed across the whole area. Non-uniformly mixing. So the pollutant doesn't disperse across the whole area. So in this case, the location is actually matter. So the examples of non-uniformly mixings are like ozone accumulation in the lower atmosphere or particulates emissions. Points versus non-point sources. So when we talk about point sources, it means that the source of pollution can be readily identified. So we can say that, well, this company is polluting the surrounding area. We can point to this company. While for the non-point sources, basically we cannot identify who the polluter is. Stationary versus mobile source. So when we talk about stationary source means that the pollution is static. So normally when we talk about a factory, the factory will pollute the surrounding area, means that the pollution is static coming from the factory. While when we talk about mobile source, for instance, pollution caused by the car or vehicles, since the vehicles is moving, so the pollution caused by these moving cars or vehicles are also mobile. This is my favorite slide because it will test your understandings. Pollution refers to the flow or stocks of harmful residual. So is zero pollution desirable or is it efficient? So we will discuss about this question during the class time. Definitely, there are costs and benefits of emissions. So there is a trade-off between these two. So efficient level of pollution is that the one that maximizes the net benefits of pollution, where the marginal benefits arises from the reduced pollution damage fall to a level equals to the marginal benefits from avoided control costs. In other words, our marginal benefit should equals to the marginal cost. This is the level that will occur if the pollution externality was fully internalized by the company. So at any other pollution level, there will be a potential Pareto improvements. So we will be using efficiency as the criteria to evaluate our pollution. Let's illustrate the flow of pollutants in a graph. The top graph is the total level of emissions, while the bottom one is the marginal benefits and marginal costs. This is the damage from pollutants. Typically, the damage function will look like this. It says that initially, the first units of pollution is not a big deal, but up to some point, the damage will be bigger. For instance, it can cause some serious health problems. So this is the kinds of the story that we would like to tell when we have a function that look like this. But in some situation, it may not look like this. So the benefits of polluting is avoiding reducing the pollutions or avoiding having to abate the pollutions. The ability to emit the first units of pollution might be very valuable or important to a firm. So the benefit will be steeply sloped at the very start. But then, as we keep going on, additional ability to pollute will be less valuable. So we will have a concave shapes. Basically, we want to maximize the net benefits, where the benefits minus cost is at the maximum. So we will have the efficient level, which is at the M star. Alternatively, we can also look at it in terms of the marginal benefits and marginal cost graph. So the top graph shows that our marginal damage is increasing while the marginal benefits is decreasing. The green line here is just to show that the marginal benefit, which is here, becomes zero at the maximum points of that benefit function. So the function will be totally flat from that green line onwards. It's just trying to show that the graph matches up. So when our marginal benefits equal to marginal cost, definitely we will get the efficient point, right? So the mu star here is actually the equilibrium shadow price of pollutions. So optimally, for the efficient solution, that is what we want the price to be, so that the firms will keep polluting until the benefits equals to the price and stop polluting thereafter when the benefit is actually smaller than the price. So naturally, the shadow price won't exist, right? So another point that I would like to share here is that our marginal benefits of polluting is equals to marginal abatement cost. We will look at these two terms in the next slide for the details. Abatement is just reductions in pollution. So marginal abatement cost is equals to marginal benefits that will be lost if emission falls. So in other words, it's also representing the minimum cost of abatements or the minimum cost of reductions in pollutions. The cool things about the efficient point is that efficient pollution level minimizes the cost of damage as well as the cost of abatement. So M star here is the efficient point. So the total damage cost is from 0 up to M star. So the area underneath the marginal damage line represents the minimum total damage cost. Definitely, the firm would like to pollute up to this point. However, at this point, the marginal damage is actually greater than the marginal abatement cost or marginal benefits. It is clearly shows that it is not an efficient point. Okay, so the total abatement costs are actually represented by the green area. So any pollution level other than the M star will give us a higher total cost. Okay. Here is my question. If the pollution level is at M instead of M star, what are the total costs? So we will discuss this question during the class time, okay? If you have this kind of graph, what is the efficient level of pollution here? And please give an examples of this kind of pollution. So based on this graph, the marginal damage, if you can see here, is extremely huge, while the abatement cost is very low. So based on the efficiency criterions, the pollution should equals to zero. So you shouldn't pollute anything. So your pollution should equals to zero. So for instance, nuclear waste or mercury waste. So the damage caused by this nuclear or mercury waste is high because their lifespan is like forever, but the cost of not releasing it is very small. Another examples of this kind of graph is like burning the household rubbish. So by burning the rubbish, it can cause a lot of cost or damages to people around us. For instance, it can release chemical smokes, it can cause soil or groundwater pollutions, while the cost of not burning the rubbish is actually very low. Just throw it in the common dustbin. Okay? What about estimating this function? So the damage and benefit function need to be estimated in advance. So the functions are normally forward-looking, so we are dealing with expected value. In reality, it is very hard to estimate the marginal benefits and marginal costs. It is hard to deal with this, right? So, well, that is the hard fact situation. This is the examples of non-uniformly mixing flow pollutants. So here there are two sources of pollutants, firm 1 and firm 2. We also have four victims or houses, houses 1, 2, 3 and 4. We also have wind blowing from many directions. So which of the houses that we prefer to live in? Ceteris paribus, holding other things constant. Definitely we prefer to live in house 4 because the wind doesn't blow to this area. Okay, so which of the source of pollution is a bigger problem here? It is definitely firm 1, right, compared to firm 2. So efficiently, we want firm 2 to pollute more compared to firm 1 because it has no impacts to the victims or to the house. Okay, if you have understood this explanation, you should be able to answer all these three questions listed here. We will discuss this question during the class time. Our main goal here is to find the efficient levels of pollution for each firms. So let's define some letters. M is the emission, A is the pollution concentration. So it could be stock pollutants or flow pollutant, it doesn't matter. J is the houses. So we can index J in a lowercase j, where one house, two house until big J. It is just the total number of houses. N is the sources of pollution, and we are going to index I equals to 1 firms, 2 firms until the total number of firms. Okay, so this subscripted by J and I is our main parameter. So basically it means that it is the marginal impacts of emission from source I at house J in terms of increasing pollution concentration. So we will assume that our DJI to be constant. So in other words, our DJI means that how much the emission from each firms are adding into the concentrations of pollution at each house. For instance, if let's say a house is far away from the source of pollution, so the D parameter is very small. However, if you are close to the source of pollution, so the D value is very high. Okay? Pollution concentration, which is A at house J, is equals to sum across all of the N sources of the emission from that source, which is Mi times with multiplier D, which telling us that how much emission adding concentration to house J. So our D here is constant. However, D can actually vary with weather and wind. So the total benefits of emission, let's put it as P equals to adding across all of the emission sources or all of the firms of the benefits that they get from the emissions. So the subscripted B with I because each firm has its own benefit function. Okay, so the total damage is actually the damage felt by the victims is a function of pollution concentration at the house. For example, our damage from pollution is how much pollution is in our house. So if you look at this damage function, basically A, or pollution concentration, has its own formula. So basically you can plug in this formula of pollution concentration into this equation so that it is easy for us later on to do the calculation. What is socially efficient emission from the sources? So the objective is to maximize net benefits. So net benefits equals to the benefits of emission across all sources of pollution minus the damage of pollution concentration felt by the victims or the houses with respects to MI. So we will use first order condition to get the efficient point. So partial net benefits over partial M subscript I will give us the marginal benefit. So this dash here is actually our first derivatives. So our second parts of the derivation, so the M is actually here, right? So we are trying to take the derivatives of this D as a functions of all these things. So we have to use the chain rule. So this D with respects to A and then D with respects to M, and it will give us this DJI, and we have to set equals to 0. Okay, so to be specific, this part here basically partial D over partial A, while this part here is partial A over partial M. So all together we will get partial D over partial M by cancel off the partial A. So this is the chain rule. Okay, now this is actually true or whole for all I, or we can say for all firms. Okay, now we can get the end marginal condition by rearranging this equation. So basically we will put the left hand side is our marginal benefits equals to marginal damage or marginal cost. So basically this is the efficient requirement, which is marginal benefits equals to marginal cost. Okay, the next point is efficient emission level will actually vary across different firms because damage vary by location. Firm with higher D is expected to pollute less because they will give more damage to the victims, right? And efficient pollution concentration, which is our A, will also vary by household. It means that house located to polluting firms has higher emission, has higher pollution concentration. Okay? Stock pollutant for uniformly mixings. So let's assume that the pollution concentration will not differ from place to place. So it means that the spatial dimensions of emission control is not important. Next, persistence of pollutant stocks over time. So it means that the temporal dimension is actually very important here. So an efficient pollution control program basically needs to focus on trajectory of emissions over time rather than just at a single point in time. So our damage, which is D, at time t is basically determined by the stocks of the pollutant, which is A. So previously A refers to the pollution concentration, but here A is our stocks of pollutants. Okay, so basically the damage is actually depends on the stocks of pollutants, while the benefits depends on the flow of emission. Okay, so definitely when the firm release emission, they will get the benefits out of it, right? So in this case, you can see that the damage is a function of stock pollutant, while the benefits is a function of flow pollutants. Emissions of stock flow relationship. A dot here is basically dA dt. It means that the rates of change of the first derivatives with respect to times. So our A dot T here is the rates of change of the stock pollutants indexed by times. So the rates of change of stock pollutants depends on the flow pollutants and the rates of decay. So if let's say the size of the flow pollutants is bigger while the rate of decay is smaller, so our A dot will be positive. Okay. alpha or the decay coefficient will vary from 0 and 1. If let's say the alpha is 0, it means that the pollutants exhibits no decay. So this is the examples of mercury and lead. Basically, they will keep building up over times. So we call it perfectly persistent pollutants. If let's say the alpha is equals to 1, it means that the pollutants fully decay in period C. So this is the examples of flow pollutants. So basically the pollutants will decay quickly. Okay, so sulfur will have higher alpha because it can decay for a week, while carbon dioxide will have a lower alpha. Okay, so normally in the real life, the alpha is between 0 and 1. So we call it imperfectly persistent pollutants. So normally the pollutant decay gradually. If we want to know the size of the stocks, we can take integrals of the A dots. So the size of A dots at time t is just the integrals of the previous functions. So t0 here is the first point in time at which the pollutants was emitted. So the pollution stock level at any times t depends on the entire history of emissions up to that time. So as the time periods are linked together through a stock flow relationship, efficient pollution targets and policy must be derived from an intertemporal analysis. Let's assume that here we have a benevolence policymaker that aims to maximize the net benefits, or in other words of saying it, maximize discounted net benefits over the long run. So here we are talking about infinite time horizon. Okay, so we have to maximize our benefit from the emissions, or we can say the benefits of flow pollutants minus the damage from the stock pollutants. So here basically we are talking about benefits minus cost. Okay, so R here is actually our discount rate. It could be socials or consumption discount rate, it doesn't matter. So the function here is exponential discounting. It means that the future in these problems or things that affecting the future is not treated as highly as we treat it now. So why do we discount? Because the value of the future or the value of dollar in the future actually worth less than the value of the dollar today, because our dollar today can be invested or put in the banks to earn the interest. Okay, so we have couples of constraints here. So the first concern is this one. So basically our stocks depends on the flow pollutant as well as the rate of decay of the stock pollutants. Okay, and the second concern is that our stock definitely should be some positive number, and the last one, the flow pollutant should also be positive. So let's assume that all functions are well behaved so that we will get, or we will able to find the maximum point. Solving optimal control problem using a cookbook. Okay, so we have to set up our current valued Hamiltonians or present valued Hamiltonians. So for those who are very familiar with Lagrangian, in Lagrangian we use it for constraint optimization in static problem, while Hamiltonian is used in the intertemporal problems or time dimension. So the first thing is that we have to write our objective function. So what is our objective? Definitely the benefits minus cost. In this case, the benefits of flow pollutants minus the damage of stock pollutants. And then we have to plus with our co-state variable here, which is mu. In the Lagrangian, we will use lambda. And then multiply with the stock flow relationship or our A dot. Okay, for those who wanted to know about current valued Hamiltonian in detail, you can just refer to your textbooks and you can find this definition. Special structure of an optimal control problems means that overall optimum is obtained if we maximize the Hamiltonians at each point in time. Okay, so we have to do first order condition to maximize these types of problem. So the first thing is that partial derivative of our Hamiltonian function with respect to the flow pollutant, and we have to set equals to 0. And the second part of our first order condition is that the rate of change of our co-state variable equals to the discount rate multiplied with our co-state variable minus partial derivatives of H divided with or with respects to the stock pollutant. Okay, let's apply our cookbook with respects to the current valued Hamiltonian function. So the first thing is that you have to write your objective function, where the benefits of flow pollutants minus the damage of stock pollutants plus the co-state variable multiplied with the A dot. Next, you have to write your first order condition. So the first part is partial derivatives of H with respects to flow pollutants, and you have to set equals to 0. So where is the M in the equation? You have it here as well as here. So partial B with respects to M plus mu, and we set equals to 0. The second part of first order condition is that we have to write the rate of change of the co-state variable equals to the discount rate or R multiplied with the mu. Okay, so in the previous one, for the cookbook, it says that minus partial H over partial A. Okay, so we have minus, but here we are talking about A with respects to A. So A is here and it is also here. So in this function, it is negative. So in our cookbook, it is negative, right? Negative partial H. So negative, negative, so you will have positive partial D over partial A plus mu and the alpha. Okay, as simple as that. So here, if you look at all this working, basically we have three endogenous variables or unknown variable, which is we have M, what else? We have A, and we also have mu. So later on, we can find or we can solve for the efficient point. Okay? To describe an efficient stock pollutants, basically time path of emission level through time should be considered. This trajectory or path consists of two phases. The first one is steady state. So in other words, it means that the emissions and pollutant stock remain constant indefinitely at some level. So we also have another condition that we call adjustment phase. So this is the case when the path by which emission move from the current level to their steady state efficient level. So this movement could be very quick or slow. So in this chapter, let's assume that we are working on or working with the steady state. Okay? In a steady state, all variables are treated as constants over time. So if you look at our function, the rate of change in our stock pollutants equals to the flow pollutants minus the rate of change in the stock pollutants. So in this case, because everything is constant, so our A dot is equal to 0 and our mu dot is also equals to 0. Therefore, our M, our flow pollutants, equals to alpha multiplied with our A. So if you rearrange it, right? So when you want to put A in front, because we want to know about the size of our stock pollutants, so you will get A equals to M divided with alpha. So this is what we call stock flow relationships. It means that in a steady state, the smaller the value of alpha, which is this one, the larger will be the stock pollutants for any given level of emission. Okay, because alpha is the rate of decay. So if let's say the rate of decay is very small, definitely our stock pollutant will be high. But if let's say the decay rate is very high, so the stock pollutant will be small. Okay? In the steady state, our mu dots will equals to 0. So time subscript become redundant and can be dropped from our equation. And thus we will get these two equations. So we obtain them from our first order conditions. So from these two equations, we will get this function. What does it saying? In the efficient solution, steady states will display these characteristics. So on the left hand side is actually the marginal benefits of emitting, while on the right hand side, it is the marginal damage of increasing the size of stocks. Okay, so we discount the size of damage by our alpha. So alpha here is actually the decay rate. So we can say that any emission to the stocks this year will decay by our alpha. We also discount by consumption discount rate, which is our R, because the damage that being caused in the future is not as important as it is now. Okay? Let me restate the steady state's efficient result for optimal control problems. So you have seen this in the previous slide. So basically on the left hand side means that the increase in the current benefit that arises when the rate of emission is allowed to rise by 1 unit. Okay, so on our right hand side is actually the present value of the ongoing cost or damage that arises when the current emission rise by 1 unit. Okay, so this is just another marginal benefits equals to marginal cost condition. That's why we will get the efficient point. Okay, what can we learn from the two results that we obtained from the steady state efficiency conditions? Okay, so basically the first lesson is that the faster the decay rate, which is our alpha, the higher will be the efficient level of steady state emissions, because when we have a higher alpha, it means that the dBdm, the left hand side, will have to fall. When our alpha is increased, so definitely this side dBdm should fall to satisfy the equality condition. And for the dBdm, it will be lower if our m is higher. Okay, so basically in this case we can say that the emission do less damage in the future because our alpha, the decay rate, is very high, so we can actually emit more pollution. Okay, the second lesson that we learn from this efficiency condition is that the larger the consumption discount rate, which is our R, the higher will be the efficient level of steady state emission. Okay, so higher discount rate means that we put less weight to the damage in the future. So we can actually increase the emission accordingly because we care less about the future. Okay? Some terminologies that you may want to know. The first one is no regrets policy. So this is the examples of programs that can create joint benefit. Okay? So when you implement these programs, you will get more benefits. For instance, when we talk about a very good abatement mission, okay, you ask the company to purchase a very good abatement mission. So what happens is that this abatement mission can reduce the pollution, and on top of that, it can also increase the productivity level of that company. Okay, so another example for these no regret policies is energy efficiency car. It could perhaps reduce congestion, and it can also reduce pollution definitely, as well as improve human health. So basically this is what we call no regret policies because we will get more benefits out of it. Okay, second terminology, rebound effects. So basically it means that the benefits are cancelled off. We believe that when we implement this policy, it will give us benefit, but later on the benefits are cancelled off because of its negative impacts. So let's look at the example. So the first one is that we have experienced energy efficiency improvements. So basically we are happy about it because we can improve our energy efficiency. So because of that, it has reduces the demand for energy, right? So this is a very good result. And when it can reduce the demand for energy, definitely it can also reduce the price of energy. So what happens is that it can free up some resources. So when your resources is available, what happens? It could result in more energy use in total because you know that the resources is there. You have plenty of resources. So people will keep using more energy. Okay? So later, you will have what you call rebound effects because later on, you will get the negative impacts of using more energy because you have free up some resources. And rebound effect actually can apply for other resources as well. Okay. We also have double dividend. It means that the revenue that we have collected from tax emission can actually be used to reduce tax distortion in other goods. So basically this will create efficiency gains. So we will get two benefits here, or double benefit. The first one, when we collected revenue from the tax emission, what happened is that the emission will be reduced. So we are happy about it. And on top of that, we will get the efficiency in the economy in terms of the increase in utility, because currently when you want to purchase your goods and services, the tax will be reduced, so you can buy or purchase more items, right? So basically this is like win-win situation. Okay.